dynamical collapse models are primarily motivated to solve the quantum measurement problem. So I'm going to just quickly review what the quantum measurement problem was. So we saw the orthodox postulates of quantum theory, and we noticed that in that sort of interpretation, there was an inconsistency. On the one hand, if you apply the collapse postulate directly to the system, then you have indeterministic discontinuous evolution. But if instead you think the system's coupled to an apparatus and everything in the apparatus, which is just a bunch of atoms, is evolving according to the same dynamical law, then if you include enough to make the whole system isolated, then one of the other postulates said that isolated systems evolves unitarily, and that's a deterministic and continuous evolution. So your perspective on what's happening to the system depends on what you choose to model quantum mechanically in that sort of approach. And then we saw this other problem between whether certain properties were determined or not. That was the measurement problem. I gave you the example of a Stern-Gerlach apparatus where you start off with the spin that's superposed Z up and Z down. The apparatus is such that it goes to indicating up or down depending on what the spin of the system is. And this was the state that gave the proponents of the orthodox interpretation a problem because it wasn't an eigenstate of observables corresponding to the apparatus indicating up or the apparatus indicating down. It was sort of mixed up between the two. And so out of all the options we discussed for solving the measurement problem, we're here now. So we're going to talk about the possibility of denying the universality of quantum dynamics, just saying no, Schrödinger's equation does not apply to all systems. And we discussed briefly on the first day something called quantum classical hybrid models, which was the idea that there should be a cut somewhere, and on one side of the cut, systems evolve unitarily, quantum mechanically, and on the other side, they evolve according to some sort of collapse dynamics or according to some sort of classical dynamics. And I mentioned that there hadn't been much success with those sorts of models. But the collapse models, on the other hand, there has been some success with. And they're very different because there's no cut in these models. They just say, look, there's a dynamics that applies to everything in the universe, whether it's atoms in an apparatus or atoms in your experiment. It's all the same dynamics. And it's different from Schrödinger dynamics. It's a slight modification on that. OK, so the idea to solve the measurement problem, you really need your new dynamical evolution law to be either nonlinear or indeterministic or both of those things. And I'll explain what I mean by that shortly. But of course, you need to, in the limit that you've got a system that's isolated, you need to recover unitary dynamics because we have good experimental evidence that small isolated systems evolve unitarily. Whereas you also need to recover the collapse dynamics in the case that you're describing some overall system and apparatus in an experiment. So those are the constraints on the new evolution law. Microsystems could undergo dynamics that's not quite unitary, but it should be unitary to good approximation so that we can understand the experimental evidence we've seen thus far. And similarly, macroscopic systems could evolve according to something that's approximately a collapse dynamics. So it's the proponents of these sorts of approaches that suggest that it's really somehow the distinction between microscopic and macroscopic that determine how this one evolution law appears similar to this or similar to that. And again, this is something I'll explain in the course of the lecture. All right, so the motivations for this sort of approach. It achieves realism. So the people who propose collapse models are not happy to be operationalists. They'd like to know what's really going on. So they think that the measurement problem really is a problem. Schrödinger cats need to have well-defined states. Secondly, it maintains the representational completeness of the quantum state. So no hidden variables are required here. And many physicists think that that's a good thing, that we should think of the quantum state as a complete description of everything there is. And so that favors this sort of approach. And then finally, there's no cut. So in line with the hope to achieve realism, you don't want to have to refer to, for example, observers. Dynamics happens differently if something's being observed. Well, that would mean that a primitive notion in the postulates of your theory would be measurement or observation. And that would not be a proper realist interpretation. So the fact that it's one universal dynamics with no mention of observers or cuts is a bonus for these people. OK. So let me start by talking about models that are nonlinear but deterministic. So the idea is that the equations that describe a measurement apparatus that's working properly and measuring spin along the z-axis were these two. Right? So if the measurement's ready to measure, then it will reliably indicate what the spin of the system that you feed it is. And that had the consequence in a linear evolution that if I have a superposition of z spin up and z spin down, I get this entangled state, which is the one that's hard to interpret. So the idea of a nonlinear modification to the laws is that when you will have these sorts of evolutions, but when you put in this state, it doesn't evolve to this. Instead, this sort of state evolves to a vector wherein the apparatus really does just indicate up or just indicate down. And it's one of the two. And it's a deterministic evolution. That's what we're postulating here. And so which it is determined by details of that initial state. So for example, it could be determined by the particular values of the parameters A and B here. It could be determined by the particular nature of the ready state that you're using. And so there'll be some particular final state. So of course, if you don't know the details of the initial state that are relevant for deciding which of the final states it is, so maybe the final state depends on intricate features of these parameters here, or maybe it depends on things in the apparatus that you don't have access to, well, then you'll have uncertainty about what the final state's going to be. So there'll be a subjective indeterminism. You won't be able to predict the outcome of this measurement based on your limited knowledge of that initial state. OK, so unfortunately, although these approaches were sort of tried out in the 70s, they really didn't have much success. So it was very difficult to find any kind of evolution law that would do exactly what you wanted to do, reproduce the predictions of operational quantum mechanics. And furthermore, as soon as you introduce nonlinearity into quantum theory in this sort of way, you get all kinds of problems. So for example, you get that you can signal faster than the speed of light using this nonlinearity. Another problem is that whereas in standard quantum mechanics, if you have two non-orthogonal quantum states, there's no measurement that can allow you to identify which one you have. But in these nonlinear theories, you can identify, you can distinguish non-orthogonal states. And so a lot of the results from quantum information theory just kind of fall apart because there's all these things you can do that typically you can't do. So you can clone things, you can it's a much different theory when you add the nonlinearity. And it's hard to see how to make it such that you wouldn't be able to use this nonlinearity to send signals and discriminate non-orthogonal states. So overall, this research program was somewhat of a failure and didn't really go anywhere. Good. The program that worked a lot better was to look at linear but indeterministic modifications of the dynamics. So now the idea is that we allow that this kind of initial state does not evolve to that entangled state, but rather evolves to one of the two states we want with some probabilities. So that's just like you would have it in operational quantum theory. But here we're thinking of these as descriptions of the real physical state of affairs. So this kind of statement is now a statement about the ontology. It's a statement about physical dynamics. So that's what the goal is. And there's a few issues you need to solve. So you want to know, so there's something called the preferred decomposition issue. You need to specify what basis collapses occur in. So remember, it's fine to say, oh, I want the basis to be the apparatus indicating up and down, but the new dynamical evolution law has to be something that applies for all physical systems, and it can't refer to whether a system happens to be an apparatus or not. It's something that you should be able to apply at the level of atoms, and then when you apply it to the atoms in an apparatus, it will hopefully entail this kind of collapse. But you need to figure out, what is it for a microscopic system? What's the basis under which collapses occur? Secondly, there's something called the trigger issue, which is more about when and by what mechanism collapses occur. So are these collapses occurring all the time, or do they occur occasionally? And how quickly do they occur? Is it sort of an instantaneous thing? All those sorts of issues. So there's various proposals of this sort, and I'm going to tell you about the Ghirardi-Rimini-Weber proposal, which is the first collapse theory that had any real success. It's also the simplest and the easiest for me to explain. This is a linear indeterministic model, yeah. And it's basically a proposal for non-relativistic quantum mechanics. So the idea is the following. Basically, at almost all times, the wave function, which is all there is according to these sorts of models, just evolves according to the standard Schrodinger equation. So here I'm imagining I've got n particles, and I'm just representing it in the configuration representation. And now, every once in a while, so every period tau, on average, a given particle collapses. Okay, so if I have n particles, then it means that on average, every period tau over n, one of those n particles collapses. And this is what the collapse dynamics looks like. So you start with the initial wave function, and you just multiply it by a Gaussian, this form, which is, centered at qk. So this is a Gaussian just for the coordinate of the kth particle. And it's centered at qk, which I'll tell you about in a second, and it has width sigma. And then I renormalize that thing, and that's the wave function at the next time. So it's an instantaneous process in this model, the collapse mechanism. It happens to one of the particles, and at least one of the particles collapses on average every tau over n period of time. Yes? Yep. So I'm not here assuming that this has to be a product state. And when I say that one of the particles collapses, I mean, I didn't mean to suggest that, find the wave function for that particle and then, apply some procedure to it. That was maybe just a quick way of saying one of the particles is chosen at random every tau period. Let's say it happens to be the kth at a given moment. Then the overall wave function of all the particles is multiplied by a function which is non-trivial only on the coordinates of the kth particle. So this thing here is multiplication by a Gaussian just on that kth coordinate. And so effectively, this is like localization to within some sort of region, some length scale sigma, and the place where you locate it is this qk, and the way that's chosen is basically by sampling at random from this probability distribution, which is also the thing that appears in the normalization factor. So this probability distribution is, roughly speaking, it's very similar to just mod psi squared. So if I want to know where should qk be, if this expression hadn't had the Gaussian in it, it would just be mod psi squared, integrate out all the other coordinates except for the kth one, and now you're just looking at the psi squared, the reduced density operator of the kth particle, and you're looking at the probability distribution over position for that kth particle. But this Gaussian kind of smears that out a bit. And nonetheless, it's still true that in the regions where the psi squared rk integrated over all these other guys is large, well, it's more likely that you're going to get collapses there. And where it's small, it's less likely that you'll get collapses. Yes?
So the slash probability is the probability that if one particular particle is selected k, then the collapse of that particle is onto the location k.
Right, or rather the mean of the Gaussian that you put into this formula is q sub k. But yeah, roughly speaking, you're localizing it to the position q sub k with some width sigma. Other questions? Okay, so like I said, k is chosen uniformly at random, and these q sub k's are chosen from this distribution. And now these two parameters, the sigma that appears in the Gaussian and the tau that determines the time scale on which these things occur, are considered to be new fundamental parameters. So from the perspective of this theory, they're just axiomatic. They're thrown in there, and I'm going to talk a bit about why they take values, why they're proposed to have these sorts of values and what the bounds on those values are. And proponents of collapse models suggest that perhaps in a deeper theory we could have some explanation of the values of these parameters. But from the level of this theory, they're just basic, and there's no explanation of them. So the tau is taken to be approximately 10 to the 15 seconds, which is on the order of 100 million years, which means that if you are, say, studying a single particle in an interferometer in your lab, and you're setting it up in a coherent superposition of going along the two arms of the interferometer, and you try to look for this collapse, well, for any given particle, you have to wait a long time. And you'd have to look at a very large number of particles to have any chance of seeing this sort of thing. And given all the noise, it's unlikely that you'd see it. So in that sense, this collapse dynamics is a very mild modification on unitary dynamics for the purposes of a microscopic system. Very hard to see that change. The length scale is taken to be about 10 to the minus 7 meters, which is a tenth of a micron, about the size of a large molecule. And the idea is that this length scale is sufficient for solving the measurement problem. So if pointers on my apparatus, the needles get localized within a tenth of a micron, then I'm happy because that's going to appear to me like a well-localized pointer. And anything more microscopic, well, it's fine if that has some coherence across space, because that's not the problem with measurement. That's not what happens to Schrodinger cats and to measurement apparatuses. So roughly that's the idea. I'll say more about this, I think possibly on the next slide. No, not yet. I'll come back to it. But this slide here is basically the whole theory in a nutshell. I've basically told you everything, roughly speaking, that you need to know about it. And then I'm going to sort of go into some of the motivations for these parameters and other ways of thinking about this. So is this clear? Good. All right, so suppose I rewrite those same evolution equations I just showed you, but I just do it in Dirac notation rather than in configuration representation. So this is the form of the Schrodinger's equation. And now the form of that collapse rule can be written this way. So it's just square root of an operator ek, which is a function of qk, acting on side t. And these guys here are basically diagonal in the position, the basis of position eigenstates. And they have a Gaussian profile. The PQKs, which I described earlier, from which you sample the Q, can, in this language, just be written as the expectation value of this E operator. This here is just a normalization factor. OK, so question is, what does this remind you of? Well, why don't I take your question first, and then I'll ask.
So why select position to collapse onto rather than another property?
Basically, they justify it a posteriori. This works because it solves the measurement problem. That's what the proponents of this approach will say. And then they might say, well, if you can come up with a different suggestion that also solves the measurement problem, then I'm happy to hear it. And I'm not an expert on this literature, but I think that there may be other proposals that may do something different from position. I think it's harder to make it work. I think there are proposals for how to do collapse in relativistic theories that might collapse in a basis of things like the fermion number. So you've sort of moved from position as an observable to just a parameter, and now you have field observables, and your collapses occur to those field observables. So that's kind of a standard move. That's sort of the equivalent of position in the field theory approach. So really the justification is that this works. And that's going to be the same justification for the values of tau and sigma. There's going to be no deeper reason.
Even though one of the motivations was desire for a realist model.
And has that at odds with?
Your answer was it works.
Uh-huh. Oh, I see. So you're saying a realist shouldn't just want something that works and reproduces the statistics. They should want some deeper reason behind it?
It would make sense to me.
Yeah, that's an interesting point. Turns out that many realists are not quite as bothered by finding kind of physical principles from which the theories follow. They're very happy to say, here's a theory. The axioms are what they are. There's no deep physical principle that leads to them. But in the context of quantum mechanics, they really want to get rid of the notion of measurement and observer and all that stuff and have a picture of what's going on in the world. That's sort of their top priority. And so if they can get that picture without having some beautiful principle that underlies it all as in an axiomatic derivation, they're happy.
I thought that at the beginning of the course we said one of the questions investigated in quantum foundations is, are there physical principles that can motivate the axiom? So that's true. I guess that question is not concerning people who are doing this aspect of quantum foundation.
I mean, sociologically speaking, there's some different communities. So in week one, at the end of week one, when I told you about the operational approach and axioms in the operational approach, that's the people who work on that is by and large quite distinct from the people who work on the interpretations I'm telling you about. So the many world interpretation, collapse theories, the Roy-Bohm interpretation, those, I mean, people have been working on these for a long time, and they haven't been so concerned with that question. What are some physical principles from which you drive the formalism? They've been really focused on what is a ontological story that makes sense given this formalism? Can we have a picture of the world that makes sense for quantum theory? But these days, with so much talk about axioms, I think there are more people thinking about trying to perhaps derive some of these approaches from physical principles. Okay, so back to the question at hand. What do these formulas remind you of? It should look familiar.
State update and Born rule.
State update and Born rule. Yes. And in particular, state update and Born rule for not projective measurements, but a POVM measurement. So this EK, QK is not a projector because the weights here form a Gaussian. They're not uniform. But it is a positive operator. And if I take all of these guys, so I sum over the discrete K index and I integrate over QK, you can show that they sum up to identity on the space of particle. So they form a POVM. And so the probability, so imagine I did a measurement of that POVM. This would be the expression for the probability of getting the QK outcome. So I guess technically this would be a probability distribution both over K and over QK. So it would pick out a K uniformly at random, and it would pick out a QK according to this guy. And if I asked how does the state update under that POVM, well, like we said in the first week, it really depends on how you measure it. But the closest equivalent to the projection postulate for POVMs was something called the Luther's rule, where you took the square root of the positive operators and you acted that on the vector number space. You might, I think I have another form. If acting on density operators, it would look like this. So instead of projectors on either side of the density operator, you have square root of the POVM elements, and then you have this normalization factor. Good. So although these guys are postulating this as a new fundamental dynamical mechanism, different from Schrödinger evolution, we can certainly think about it as an operationalist would. We can say, well, it's equivalent. We now have a way of describing what they're postulating. They're saying this we would normally describe in an operational theory as a kind of fuzzy measurement of position. So it doesn't resolve position perfectly because these Gaussians all have some variance. So it's sort of you get a noisy estimate, partial information about the position. And then there's this particular sort of collapse rule, which tends to localize things after you do this measurement of position. And basically, the collapse theorists are assuming that although you aren't doing a measurement on the particle, basically spontaneously, every 100 million years, every particle does get subjected to one of these measurements and gets localized somewhere. That's the idea. All right. If you happen not to register, say we were doing the operational one, and I happen not to register what k and qk I got as a result of the measurement, then the collapse rule would just be this, but summed over k and integrated over qk. And this sort of dynamics tends to add noise. If I start out with a pure state, and then I apply a measurement and I don't register the outcome, then typically I have a lot less information afterwards because I've decohered in some basis. Here I'm sort of decohering relative to this fuzzy position measurement. So this, of course, fits the general form of non-unitary dynamics that we talked about in the first week. So I mentioned that a general transformation was a trace-preserving, completely positive linear map, T. And every such map always could be written in this Krauss form, where these A mu's were arbitrary linear operators. A mu's were just, A mu daggers were just their adjoint. And those A mu's had to satisfy this condition here. Well, this Luther's rule collapse map here satisfies that definition. And so it's an example of one of these guys, which means that we know, we can now see that because these things were convex linear, so they, if I have a mixture of inputs, I get the corresponding mixture of the outputs. They took positive operators to positive operators, and they were completely positive. But they were trace preserving, so they took normalized operators to normalized operators. And finally, they were completely positive in the sense that if you acted on half of an entangled state, which is a positive operator, you still get a positive operator coming out. So the dynamical collapse law that people have assumed doesn't violate any of those properties, which is good because if it did, then you would end up with predicting probabilities for measurements that are negative or greater than 1. And so part of the reason it works nicely is because it's a dynamics that already exists within the operational framework. It's just not the standard unitary dynamics. Incidentally, I guess I didn't say it explicitly here, but the reason it's linear is because this equation here is certainly linear in psi of t. If I have a coherent superposition of terms here, I get the same superposition of terms because this is just a linear operator acting on it. All right. So let's look at a simple example of this theory in action. So suppose I just have one particle. It starts out in a wave function that's doubly peaked. So I'm going to imagine phi a is a kind of Gaussian centered over here. Phi b is a Gaussian centered over there. And I have a superposition of those guys. So now I choose at random some position q from the psi-squared distribution. So I'll choose q, and suppose it happens that I've sampled it here. Then I multiply this guy by this Gaussian, throw in the width sigma. And what's going to happen is I'm going to get something that looks roughly Gaussian. It's not quite Gaussian because this function isn't uniform over the support of this guy, but it's a slightly distorted Gaussian. And then it continues to evolve according to the Schrodinger equation. But the interesting thing happens when you have multiple particles and they're entangled. So imagine we have the same sort of scenario, but now we have two particles. I'm going to imagine each of them is in 1D. And they're entangled in this way. So phi a and phi b are the same sorts of wave packets we saw there. And chi a and chi b are also going to be Gaussians, with chi a close to the origin and chi b further away. But now they're correlated in this way so that in the 2D space, I have peaks here and here. Now suppose that just one of those two particles collapses. So suppose it's particle 2 here. And again, I just find the center by choosing it at random from the psi-squared profile along x2. So say I get this one here. Then I multiply by this function on x2, but I don't do anything to the x1 coordinate. So it's just uniform over that coordinate. And the point is that if this second peak basically lies entirely in a region where this Gaussian has almost no amplitude at all. So it gets almost completely suppressed. I mean, there's some perhaps tiny amplitude left over, a very tiny peak here in the wave function. But this has happened even though only the second particle has been subjected to this collapse mechanism. But because of the way entanglement works, because of the correlation between the two particles, the overall wave function gets reduced to just the first term. So it's a bit like what we saw in the steering phenomena, where if I update my information about this system, then I learn something about some observable of the other system. Well, here in this, and I'll collapse. Like if I have 0, 0 plus 1, 1, and I measure the 0 state here, I'll collapse to the 0, 0 state. So that's just effectively what's happening here, but relative to this position basis. Yes?
I'm a little confused by the notation. So there's what sort of varies is x1, x2,
Nope.
a and b, and phi and chi.
Yes?
Are x1, x2 like coordinates in one single space, as in
Yes.
physical
So
space?
if imagine you have a one-dimensional space, you have two particles. X1 is the coordinate of the first particle. X2 is the coordinate of the second particle. And I'm just using phi to mean these are the wave functions of the first particle. Chi's are wave functions of the second particle. And the difference between phi A and phi b is that they're just wave functions located different places. So this wave function here is a wave function on configuration space. It describes where in the 1D physical space each of the particles lies. But because they're correlated, and because wave functions for multiple particles don't live in real space, phi x1, x2 is just functional configuration space. Yes?
So all throughout here, we're assuming that the probability at any given time of particle K undergoing this collapse is completely independent of what environment it's in or what else it's entangled with or what other state it's in. How do we sort of have the right to assume that? Like, do we just assume that because it's the simplest model? Or
I think the proponents of this approach would say, look, that's the paradigm in fundamental physical theories. If I tell you, this is the Lagrangian of the universe, these are the equations of motion, Newtonian mechanics works like that. It doesn't matter if your atom is part of a star or, part of a doorbell. It's going to behave according to, the fundamental laws, the same laws. And that's actually what we want. We don't want to have to specify whether the context is something isolated from an environment or not to tell you how it acts. Its environment may, by following these fundamental rules that apply to all microscopic systems, might influence it, but that's not going to be part of the prescription of the laws.
So even if, let's say, we had a completely empty universe except for some single particle sitting in it, that single particle would still just
occasionally,
spontaneously
every 100 million years, it would collapse somewhere. That's the idea, yeah.
It's hard to get my head around. Okay.
Yes.
Also, so then the psi is then the real thing for the GRW people, but then if it's the final configuration space, then how is that?
Yeah, that's a good point. You're saying, look, they want realism, but the only object that they've reified is the wave function, and it lives on configuration space, not real space. So how are you going to get a picture of what's going on in real space, physical space, starting from that kind of ontology? Yeah, that is a problem, and there's been a few different proposals for how to deal with that. I have a slide on it. Let's see, is it coming up soon? No. Well, why don't I say it now, and then I can just skip over it later. So one idea was that you just use kind of the mass density. So you say, let's calculate the mass density based on this wave function. And because of these collapses, things tend to be less entangled than you would have otherwise. So in this example, I got something that isn't quite a product state because there might still be some small amplitude over here, but it's pretty close to a product state. And so I can almost think of it as sort of two waves living in physical space. And so they say, well, why don't you just take the mod psi squared, and that will tell you sort of the mass density for each particle, and that's how you should picture what's going on in reality. Others have said, well, you can't just ignore these small tails. They're really there according to the interpretation. And there's some small probability that maybe the next time you do this collapse, actually you find the particle over here. Even though that's as highly suppressed, there's still some probability of finding things over there. So this mass density picture kind of can't do justice to the fact that there are still these tails around. That's the kind of criticism that this sort of approach has seen. And there are responses to that, which I'm not really an expert on. There's a totally different kind of a response, which is interesting. This one was proposed by Bell. He was saying, well, let's forget about the wave function. Instead, imagine that if you have a space-time diagram, every time a collapse occurs, there's kind of like a little flash at that point in space-time. Okay, so if there's a collapse which occurs at random here and at some particular location, then I put a flash there. And I just draw all the flashes. And Bell argues that those flashes alone already have a lot of the structure of the wave function encoded in them. So a pointer, which has a large number of particles in it, there'll be flashes going on in it all the time, which will kind of pick out a space-time tube of the pointer. And because the entanglement has been eliminated, that pointer, that set of flashes, is going to evolve kind of classically. So I can sort of think of the flashes as a new kind of atom, which is just sort of localized, not just in space, but in time as well. And the sprinkling of those guys specifies all what's happening in the world around us and how things are evolving. Yes?
Okay, I think I've pinned down what's really bothering me about this. Okay, what's bothering me is that this requires every particle to have its own little internal clock with like an absolute Newtonian kind of time to it, like some sort of time that on that particle's clock ticks along, and that time is defined relative to what? Like it's the Newtonian absolute time.
I think this sort of model does assume an absolute time. I don't think it's much different from what you'd have in Newtonian mechanics. I don't see why every particle would have to have kind of like a separate clock. You just imagine time goes along, and then a dice is rolled, and some unlucky particle gets chosen from the lottery to be the one who suffers the indignity of collapse.
Okay, I guess what I mean is, like, let's say you boosted a particle so that it moved very, very close to the speed of light. Would that extend its lifetime through which it can avoid undergoing collapse? Sort of like if you have like a cosmic ray muon, which has a certain chance of disintegrating, right? It makes it through the Earth's atmosphere because you boosted it so much that its lifetime gets extended. So then in this theory, I guess I'm thinking if the probability k is kind of uniform, then we're saying that accelerating something shouldn't extend its lifetime to avoid collapse, which means there's some sort of notion of time that's not tied to the relativistic time. In which case, it's an absolute Newtonian time. So that's what's bothering me.
Got it. So I should put a caveat in front of what I'm just about to say. I'm not an expert on relativistic versions of collapse theories, but there are relativistic versions of these. And they have the same kinds of features that the relativistic versions of Bohmian mechanics had. So for example, one thing you'll notice is that when I imagine I have two particles and they're separated in space, and this one collapses. Well, it affects the whole wave function. And so, for example, if there's some spin degree of freedom of that particle over there, and it's in a superposition of two different spins correlated with being in two different positions, and then I collapse that guy's wave function by virtue of a measurement I did on something entangled with it, well, then I change its spin degree of freedom, for example. So I've changed its properties instantaneously, and so I have a failure of Bell's notion of local causality, which, of course, we know we have to have in any realist model. But it also means that in this sort of collapse model, you have to specify in what reference frame are these collapses occurring instantaneously. And there have been, there's a whole literature on this sort of thing. So one approach would be, okay, there's a preferred rest frame. It's hidden from us, like in the Bohmian case. So we don't see it at the operational level, but it exists. It determines when collapses occur. It determines the preferred notion of time relative to which these collapses occur at every 100 million years. There are other proposals that I don't think have been sort of cleanly kind of wedded to the story I've told you. But there are proposals that say things like, oh, the collapse should occur along light cones, like maybe along the backward light cone of a collapse event. And I'm not sure what those proposals would say about how how much time is there between collapses for a particle based on different velocities? I think it's an interesting question, and I don't know the answer to it. Okay, other questions about this sort of thing? This is really this second half of the slide here is really what's critical for getting these sorts of models to solve the measurement problem. Okay, so I already said that we have a failure of local causality. So let me just go back to the measurement problem and show you how that works. So if we have an apparatus, this is my system, and then I have an apparatus that has many parts in it. So it's made up of many atoms, for example, M of them. And the whole thing's gone out into this entangled state where the apparatus has a pointer, but it's not indicating up or down. It's in this superposition of those possibilities. Well, just as we saw in Bohm mechanics, for typical kinds of apparatuses, what you find is that these wave functions, chi-A and chi-B, are not merely orthogonal in Hilbert space, but they tend to be disjoint in physical space. So for example, if I think of these, this needle pointing to the left and pointing to the right, then each of the atoms in it is, you can think of it as kind of localized in a wave packet, and it's either here or here. And so for each of those atoms, say the kth atom, I'll actually find that the product of these two wave functions, when I look at just the kth coordinates, they have almost no overlap in space. And so if I happen to collapse the kth particle, then it would basically have amplitude 0 either in the support of chi-A or in the support of chi-B. Because wherever it gets picked out, one of those two guys is going to have amplitude close to 0. And so it's going to set the whole term to something close to 0 if just the kth particle collapses. So essentially, the wave function gets localized in all the coordinates, even though only one of the particles has been hit. And then if you ask, well, what's the probability that it's going to localize to this term? Again, you have to look at the rule of how do I draw that position at random? How do I decide whether it's in the support of this guy or the support of this guy? And it's not hard to see that ultimately it's going to be given by alpha squared and beta squared, because no matter which particle I'm drawing, I just ask to sort of I multiply this guy with the Gaussian, and whichever one of these two guys has overlap with that Gaussian, well, I integrate him up, and I'm left with the alpha squared. So that's good, because this is what we wanted. We wanted it to go into one of the other positions with the operational probabilities. And now here's the really critical thing, that if your apparatus is big, if it's got lots of components, so say it has 10 to the 20 particles in it, then although every one of those particles only collapses every 100 million years, if you ask how long do I have to wait for just one of them to collapse, at least one of them to collapse, then it's hardly any time at all. So in this example, it's just 10 microseconds. And then one of them collapses, but then the whole wave function gets changed, and one of these terms effectively goes to 0. So this is the kind of magic by which these guys achieve, on the one hand, a good approximation to unitary dynamics for microscopic systems, and a very good approximation to collapse dynamics for macroscopic systems. They're relying on sort of the way that collapses act on these highly entangled states. Yes?
So I think you're implying that it doesn't work then for if you have orthogonal states that have considerable overlap in space? But does it still work then? Does it work less well?
If you had if you had a macroscopic system and it went into one of two wave functions, but those wave functions were non-disjoint in the coordinates of almost all the particles in those guys, then yeah, this collapse mechanism would not cleanly sort of push you into one of those two terms. It would leave you with a superposition like this. But the argument of proponents of this theory is that that's not the way the measurement apparatuses we build work. It is almost always the case that if you look far enough down the line, you'll see that the information about the system has gotten encoded not only in something that goes into one or two areas of space, but many, many things that go into one or another area of space. It is exactly the same thing that the Bohmians relied on, because their Bohmian positions picked out a kind of an occupied wave and the others were empty waves, as long as those supports were disjoint. And when we argued that we had irreversibility in the Bohmian approach, the effective collapse, so for them, the Bohmians, you don't have a real collapse mechanism. You just find that the dynamical equations for the particle only rely on the occupied wave after a certain point in time. And as long as there's many, many particles that have become spatially disjoint, it becomes really hard to reinterfere all those. And so effectively, you have irreversibility. But the property that you need for the environment and for your apparatus is the same in both cases. You need to have redundant encoding of the information about the system in a spatial degree of freedom that becomes disjoint. Other questions? All right. So the idea is that we can recover the projection postulate from operational quantum mechanics. But furthermore, now we can say that this apparatus really does get the properties it should have, because the final quantum state is an eigenstate of observables like, needle pointing left and needle pointing right. These states are eigenstates of that observable. That's what we wanted. So what about these parameters? What happens if I make the time interval between collapses too big? Well, if instead of every, 10 to the 15 seconds, if I made it 10 to the 20, 10 to the 100, then I might find that even though I have a very large apparatus with Avogadro's number of components in it, nonetheless, it doesn't collapse quickly. And that would mean that these coherent superpositions in Schrodinger cat states would persist for too long. And we would not be able to explain why we observed a particular outcome. The problem with making it too small is just that all those tabletop experiments I was thinking about earlier, where you're doing an interference experiment, if on the time scale of that sort of experiment I expect my particle to collapse before I've reinterfered it, then I wouldn't expect to see quantum theory vindicated in those sorts of experiments. I wouldn't expect to see interference. I would expect that as soon as I made the interferometer big enough, I would start seeing this kind of decoherence, which I couldn't account for by virtue of my model of the environment of the particle in that experiment. I would have to say, oh, there's some extra decoherence here. And that's not what we see in the lab. So that constrains tau to be somewhere between those two extremes. And this 100 million year figure is chosen to avoid those two situations. The same sorts of comments can apply to this width of the collapses. So if you made sigma too big, so that the needle on my apparatus could go into a superposition of pointing left and pointing right, because it doesn't get localized to within the width that it needs to be localized to. And the problem with making it too small, you might say, well, that's make it even smaller, then things will be even better localized. But there's a problem there as well, which is that, strictly speaking, this collapse mechanism adds energy to the system. So I didn't say it explicitly, but by positing that things get localized every once in a while, you actually tend to increase the kinetic energy of the system. So if I have a wave packet that's spread out, it has a very low kinetic energy, I localize it to a Gaussian. The kinetic energy is given by the gradient squared. And so I tend to increase the kinetic energy by localizing it. And it means that these collapse models posit that the universe is slowly heating up over time. But the amount of the heating is incredibly small, and you ought not to be able to detect it, given the parameter sigma that they've chosen. So they admit that there's this heating, but it doesn't empirically rule out their theory because it's so small. If, however, they've made this sigma parameter much, much smaller, then the heating would be a lot greater, and you would expect to see it. So for example, atoms, the electron in an atom, if it got localized to a very small width, well, then that tends to increase the probability that the atom will ionize, and I should be able to see that. So if you make sigma very small, you're going to have more of these anomalous ionizations of matter and heating that you'd expect to be able to measure. So I recall that some people who were working on this had an experiment that they were suggesting that involved the Sudbury Neutrino Observatory, because they're very sensitive to ionizations and heating effects. And so if you saw sort of anomalous heating there, then you might be able to attribute it to a collapse mechanism. All right. So if you ask, well, what is the experimental status of these sorts of models? It's a difficult thing to do. It's a difficult thing to test these models versus just unitary dynamics. And the main reason is, well, this anomalous heating I just mentioned, that's hard to detect because it's an extremely small effect in the models that have been proposed. But if you try to do a more direct test, so you say, look, let's just prepare one of these entangled states. Let's make it so that, say, the number of components is not so huge that it collapses really quickly, but let's just make the number of components large enough that we expect the collapse time to sort of fall down from 100 million years to something within a time scale that we could hope to measure, like maybe on the order of seconds, let's say, in the lab. That's still a large number of systems to do that. And the problem is that as soon as you get a large number of systems and you try to prepare them in a pure quantum state and verify that that state remains pure and evolves unitarily, you have to isolate them all from any environmental interactions. Because if I have to say one of the particles in my n particle system, if just one of those particles interacts with an environment particle, that environment particle could carry away information about its position. And that would have exactly the same sort of signature as this collapse mechanism. The collapse mechanism says, look, there's no environment particle that's carrying away information. There's just a fundamental new dynamics on that Kth particle. But it would look the same experimentally as if that Kth particle had interacted with its environment. And so isolating large systems from their environment is a very hard problem. If we could solve it today, we could probably build a quantum computer. And we can't do that yet. So in general, it's not an experiment that we can do easily. Although there have been many proposals for how you might push that limit out and have larger and larger numbers of systems prepared in pure entangled states and isolated from their environments for longer and longer periods of time. But we're still not so near to where we'd be able to test these sorts of collapse models. Questions? Good. Let me mention just a couple of other topics. There is an alternative collapse model due to Philip Pearl. So Philip Pearl is a guy who spent his entire career working on these dynamical collapse models. And so he was very impressed. He was the guy who was working on those nonlinear deterministic models I told you about in the beginning, in the 70s. And then this GRW model, the paper came out in about 1985. And so when Pearl saw that, he started working on these linear indeterministic models. And he didn't like the fact that the GRW model made collapses into these discontinuous events that occur every once in a while. He didn't think that that fit well with the sort of paradigm of modern physics. So he wanted something that was a continuous collapse mechanism. And so I'm not going to go into the details of the model, but I'll just sort of I'll give you the rough idea for how it works. So collapse in his model is a continuous process, which is governed by some randomly fluctuating field now. So rather than just sort of these random numbers that are generated, you have a random field. And roughly speaking, the way it works is that the different branches of the wave function effectively play a kind of game. But let me describe the game to you, and then I'll say what happens to the wave function. So there's a game called Gambler's Ruin, where you have two people. Let's say they have $100 between them. And one of them starts with, say, $80, and the other starts with $20. And then the game is they flip a fair coin, and if it's head, Alice gives $1 to Bob, and if it's tails, it goes the other way. So the amount of money they have kind of fluctuates randomly up and down. And the game ends when one of them has all the money, and then the other person can't play anymore. So the guy who has $80 could lose because he could sort of get unlucky and everything fluctuate down to zero. But you've got a bigger reserve with $80, so you're less likely to fluctuate down to zero than the other guy is. And if you just ask, well, what's the probability that the one who started with $80 wins this game? The answer is 0.8, and the probability of the other is 0.2. So basically, what this sort of model does is it says, OK, we have these two branches of the wave function. Let's take a simple case where there's just two branches, with weight alpha squared and beta squared. And then you have this continuous process whereby some amplitude moves from one branch to the other at random, either in one direction or the other. because one of them has a sort of larger reserve of amplitude, it's more likely that at the end, when one of them loses all of its amplitude to the other, it's the one that started with the larger amplitude. And so the probability that you get the second branch finally is just given by the mod squared that it started with. So that's the sort of thing that you want, that the probability of ending up in one branch is the mod squared of its amplitude. And you can generalize this to more than 2 branches. And you can write down equations for how it all works. But that's the basic idea. All right. Well, you could go look at Philip Pearl's papers if you're interested in this. OK, so we've talked a bit about some criticisms of this approach. So what is what is the ontology in space-time? If it's the wave function that's real, but that lives in configuration space, and you want some picture of what's going on, is it the mass density on space-time? Is it this flash ontology that Bell proposed? Both of them are a very significant departure from any kind of classical worldview of what's going on. And there have been sort of a lot of disputes about whether either of them really makes sense. I mentioned that you've got this failure of energy conservation in these models. You have a slow heating. So one criticism you can make is that energy conservation is a principle that seems to have served us well. It's a feature of all the empirically successful theories we've had. Does it really make sense to give it up here in a kind of seemingly inelegant way? There aren't any really deep physical principles behind this failure of energy conservation. Ultimately, the features of this model are chosen all in the service of trying to solve the measurement problem. It's kind of all justified a posteriori as we need to solve the measurement problem. As I mentioned, it's really unclear whether you could hope to maintain Lorentz invariance for some relativistic versions of collapse models. As I said, there's various proposals about collapses along light cones and things like that. And I'm not an expert on the field, but my impression is there's certainly no proposal out there for which there's any kind of consensus. Yes, this is a good way to do a relativistic collapse theory. So all I can do is say, if you're interested, go look at some of the recent literature on collapse theories for relativistic quantum mechanics. Then the final criticism I want to spend just a little bit more time on, and it comes back to something I mentioned in the very first week of the course, which is basically that the experimental signature that proponents of collapse theories say would vindicate their models actually can be explained in other ways. So even if we saw some anomalous decoherence, right? So what I mean by that is, suppose you set up an experiment, you found a way of preparing a large number of microscopic systems in a coherent state such that they were entangled, and the 2 branches were kind of spatially disjoint. So let's say you did all of that. You feel that you really understand the environment of your system, you've got it all well modeled, and then you measure the decoherence rate, and you find that it's higher than it ought to be given your model of the environment. So you'd say, OK, there's some anomalous decoherence here. And then you could say, does it fit with some of these prominent proposals for what the rate of decoherence we should expect to see according to collapse? So say you've done all that, and you've found some anomalous decoherence. The problem is that that is also consistent with a different hypothesis about how we should change our fundamental model. And that hypothesis would be that there's some extra degrees of freedom we didn't take into account before. And we're just coupling unitarily to those. So let's see. This collapse map that we described earlier in the lecture, it, as I said, is one of these trace-preserving completely positive maps. But what we saw in the very first week is that every map of this sort can always be modeled by a unitary coupling to some ancilla, which we then ignore. So I think I have, that was called the Stein-Spring dilation theorem. Yeah, I have a picture of it here. So this was, in the first week, I sort of emphasized this kind of parallel between preparations, measurements, and transformations, which is that if you have a density operator, it's always possible to find a purification of it, which means it's always possible to make a preparation associated with that density operator, wherein you prepare a pure state on 2 systems, S and A, and then you throw away the A system. So call that a purification type preparation of that mixed state. And similarly, I mentioned that for any POVM, it was always possible to sort of measure it by doing a projective measurement on S, your system of interest, and some ancilla prepared in some state chi A. And so the analogous thing here was that for any trace-preserving completely positive linear map, you could always implement it by coupling your system unitarily with some other system that you've prepared in some state and then ignoring it. So that means that in the case of the collapse models, when I see this anomalous decoherence and I say, oh yeah, okay, it looks as if it corresponds to some completely positive map, and maybe it's even close to what the collapse theorists have proposed, I can always say, well, the lesson I draw from that is that there are some other degrees of freedom out there which we haven't previously taken into account in our theories. Maybe they're local to the system I'm interested in. Maybe there are internal degrees of freedom that I hadn't noticed before, or maybe there's some kind of cosmic ray that's coming in and interacting with it, which I didn't know before. But it's interacting unitarily, and it starts off in some state, and I'm not paying attention to it, and that is why I'm seeing this decoherence. So by virtue of the Stein spring dilation, it's very hard to ever make an argument based on experimental evidence for this anomalous collapse mechanism as a new sort of fundamental type of dynamics, as opposed to this sort of thing. So the arguments would have to appeal to maybe the simplicity of the two hypotheses or the aesthetics of the theory. I think most collapse theorists would say, but if you do it this way, you haven't solved the measuring problem, right? That our whole motivation was to solve the measuring problem. And now you're just saying, I've got unitary dynamics on a larger system, so you're still going to have Schrodinger cats, and you're going to have pointers going into superposition states. And then, of course, the response could be, I would prefer to solve the measurement problem some other way, not by modifying the dynamical equation law, but maybe by introducing hidden variables or doing something else. So it kind of boils down to an argument about what the best way to fix the orthodox interpretation is. OK, so this is my final slide. In both these models that I've talked about, GRW and continuous spontaneous localization, the sort of important feature of an object that led to it having more of a collapse dynamics, a projection postulate type dynamics, rather than a unitary dynamics, was essentially the number of fundamental constituents that made up that object. But other proposals that are out there focus on other properties of systems. So I'm not going to say very much about these. So there's some ideas out there that, in particular, Penrose has talked about these, that it might be the gravitational field induced by an object that's relevant to the rate at which it collapses. So the idea would be that the more massive an object, the more quickly it collapses. So microscopic objects evolve unitarily by virtue of their very small mass, and macroscopic objects evolve more like projection postulate by virtue of their large mass. And then another set of ideas associated, for instance, with Tony Leggett, is that it's not the compositeness, just the number of constituents, but somehow the degree of entanglement or the complexity of the quantum state of those systems, which is ultimately relevant for determining what kinds of dynamics it undergoes. And to my knowledge, neither of these sorts of ideas have been turned into a fully explicit proposal of the sorts we just saw that really make definitive predictions. These are more just suggestive ideas for a research program that would develop such a model. And again, it's really the motivations for the people who propose these is to solve the measurement problem while maintaining realism and the wave function being the description of the state. Yeah, so that's it for collapse models. Questions about that? Yes?
Maybe it's actually a more general question, but I suppose that if you think about it, even a normal atom is probably entangled with a bunch of other systems, maybe even just the electromagnetic fields around it, for example.
Mm-hmm. Mm-hmm.
But with that reasoning, you would expect no quantum behavior at all, because everything would be decoherent, or in this model, everything would collapse because everything is connected to a much larger system. And then you would kind of... So, like what we think are isolated systems are in effect actually tangled with much larger systems. In principle, I suppose. In principle, everything is.
Well, some of that kind of entanglement that's out there might, I mean, you're suggesting that, I'm not exactly sure what you're suggesting, but it sounds as if you're saying you'd think that we'd see less interference than we do because systems are becoming entangled all the time with other systems.
Right.
Because they're interacting with other systems. So, one way to ask that kind of question would be, if I have a Mach-Zehnder interferometer and my systems are, being put onto, through a beam splitter and then recombined in another beam splitter, after bouncing off mirrors, and I see interference, you could kind of ask, well, what about the photon bouncing off that first beam splitter? Didn't that beam splitter carry away information about the photon, decohere it, figure out which way it went, and destroy the interference? So why do I model a beam splitter by an external potential, which induces unitary evolution on the particle, as opposed to modeling it as a system which couples in a way that carries off information and becomes entangled? So even if I choose to model it quantum mechanically rather than external potential, there's a difference between their evolution sort of staying product and their evolution becoming entangled. And if it's entangled, then you expect to see this decoherence, and if it remains a product, you expect to see coherence. And that is exactly the kind of question that you're going to be looking at this afternoon. So I hope that your question will be answered in tutorial. And ultimately, it depends on kind of the nature of the unitary. So it's just, for those situations we tend to describe as external potentials, it's by virtue of the kind of unitary that actually describes that coupling. And the sorts of things that do measurements are a different unitary. So, I mean, I'm not thinking of the particle interacting with its electromagnetic field. I can't think of what the explicit model there would be. But it's going to be the kind of unitary interaction which isn't going to carry information away about the particle that will say, collapse its orbital into some localized position. The field is just not going to carry information about exactly where the particle in its orbit is. So that's why it's not going to, I'm still going to see that kind of coherence in the atom. Yes?
Just because my knowledge in quantum optics isn't a lot, but I know from what I understood, they use some crystals that have nonlinear behavior. So in that context, how would then a linear kind of description be? How do you capture that kind of non-linearity into a linear model like quantum mechanics, for example? Then don't you have to introduce some kind of inconsistency? I don't know, or some partition kind of theory.
So it turns out that kind of nonlinearity, so like what people talk about when they talk about nonlinear optics, does not translate in the quantum language into an operation which maps a vector on Hilbert space nonlinearly to some other vector on Hilbert space. So it's and the kind of nonlinearity in optics is something where you have an effect that doesn't depend on the number of photons you fit in, but the square of the number of photons you fit in, for example. And if you imagined doing a measurement of photon number and then doing some process conditioned on the outcome of that measurement, I could easily, within the operational quantum framework, sort of devise something that would respond as the square of the number rather than linearly with the number, without ever getting outside of the framework of operational quantum theory. So even though all my maps would still be trace preserving completely positive linear maps, so now they're kind of linear on the space of operators, rather than, so in this lecture we were talking about linearity on the vectors of Hilbert space, but in the first week we were really talking about linearity on the space of operators. So nonlinear optics is linear in both those senses. It's the transformations are linear on the space of operators. If it's a transformation on pure states, it's linear on the pure states. But in terms of the photon number that I feed into a device, I can have an effect which depends not linearly on the photon number. Did I answer that adequately, or?
So you're saying somehow we can capture those non-linearities using linear operations. Is that by coincidence, or is it just that it works with operational? I mean, yeah. Is that like useful operationally, or then like we try this and then it tallies with experiments, or that that's actually a more, it's a stronger basis that why it works.
I feel like there must be sort of a really efficient way of answering this question. Yes?
So,
Yeah, go ahead.
so in that case, it's still Hamiltonian evolution, so it's still unitary. The thing that's nonlinear is the Hamiltonian. Is nonlinear in some parameter of the system. So it's not outside of quantum mechanics at all. It's still unitary evolution. It's just that the Hamiltonian is nonlinear in photon number or whatever. That's the sense in which it's nonlinear. It's still Schrodinger equation. Is that?
Yep.
Okay.
There's another way of saying that. Hey. Like if I think of a computation, right, it takes some bits in and it evaluates a function on them and outputs that. Okay. So I can say, let me think of that computation in terms of what sort of function it computes. So if I feed a bit in, or 2 bits in, then the linear functions on bits would be things like sum, which in the context of logic would be like an OR operation. So 0, bit A plus bit B. If I have the addition table would be 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0 because it's just addition mod 2. So addition mod 2 is a linear operation as a function, and so is the NOT gate. It doesn't require me to do any multiplication of those bit values. But a gate that took in a bit A and a bit B and output A times B, whose the multiplication table now is for all bit strings except 1, 1, I get 0, and for 1, 1, I get 1. That's nonlinear because it requires me to take products of these guys. So you can say, all right, there's a difference between linear gates and nonlinear gates in the computation. But if I now think about those gates in terms of classical probability theory, and I say, I have some probability distribution over the input strings. And then I know it gets fed through the gate, and I want to say something about the probability distribution over the output strings. Now I ask about linearity in the following sense. Is it convex linear? If I take a mixture of 2 probability distributions over the input string, do I get the corresponding mixture of output distributions? And the answer is yes. For any function, you're going to get the mixture of the function of the inputs. And so you see how there's sort of 2 different notions of linearity going on in that example. And so all I'm trying to say is that the nonlinearity in optics is like the nonlinearity of the function you're evaluating in that computation, whereas the linearity of the completely positive trace-preserving linear maps is like the convex linearity of classical probability theory. Okay.